physicist working for Block Oil Mid East with Gurna 2 project, Basra, Iraq. Our webinar today will be with Mr. Nicolas Kotlar from KAPPA Engineering Company in regards to like conventional production logging tool and how we utilize its data in the Emeraude software. And there will be another webinar this year also in regard to like, let's say, multi-array production logging tool. Just I will show, what is the share screen? Just I'll share my screen for a second. Okay, so this is our third webinar for this year, and we plan to do 10 webinar for 2024. All of them is focused on production logging with manufacturer and with software provider as well. We will have both sides. I would like to thank all our sponsors company that will support us in 2024. As usual, for any attendees that will attend more than 6 webinars, you will get a special certificate. And if anybody will appreciate if anybody willing to change his chapter to Iraq chapter or renew his membership. Okay. Mostly we'll keep the question and answer to the end of lecture. Okay. And I will keep the mic for Dr. Mohammed.
Yes, Mr. Mazen and Mr. Nicholas and our dear attendees, hello again. This is Mohammed Jawad Zainul Abidin, Senior Faculty Member at Petroleum Engineering Department, College of Engineering, University of Kirkuk, and the Vice President of Technology in SPWLA Iraq chapter. Iraqi chapter SPWLA would like to introduce to you the third webinar in 2024 regarding conventional production logging analysis utilizing Emeraude software by KAPPA Engineering Company. Today we'll again Mr. Nicolas Kotlar will be with us and to introduce this lecture. We hope to spend a good time with SPWLA Iraq chapter today. Thank you.
Thank you. The mic for you, Nicolas. Thank you, Doctor.
Okay, thanks, Mazen. Thanks, Mohammed. And thanks for having me today as a presenter. It's my pleasure. And I'm going to start sharing my screen. Can you see my screen?
Yes, crystal clear.
Yes.
Good. Excellent. Okay. So let's get started. Nicolas Kotlar again. My email is here for any question or any comment on Emeraude or on the subject matter of production logging. You can contact me directly. So let's get started. So for today, we will be using Emeraude. Maybe if you have been using Emeraude for a number of years, you probably have seen a bit of a transformation. We went from production logging software only to an integrated casehole logging platform. Many of you would recognize some of these images here, some cement evaluation logs, impedance, VDLs, internal radius, thickness, spectral noise logging. You can see 3D and so on, right? So Emeraude is not just a production logging software, but it's an integrated casehole logging platform. As mentioned, the areas up here that we handle are production logging for vertical and horizontal welds, the array tools, DTS and thermal-based interpretation, multi-finger caliper or any internal radius measurement analysis can be ultrasonic as well. Spectral noise log, pulse neutron logging for water saturation behind casing, cement bond locks, any type, sonic, ultrasonic, segmented, and so on, electromagnetic and ultrasonic thickness, and reservoir description. Okay, so these are all the areas. Today we will focus on the production logging, and especially the ones used for vertical or slightly deviated wells that use conventional tools. Okay, so just to recap why we are here, why production logs, and what do we want to achieve. So here you can see a typical well completion, for example, with 2 perforated intervals, a tubing casing here. And if we are lucky at surface, we will have surface rates, total commingled production from these 2, 3, 5 perforations or reservoir intervals, right? But here we get surface rates depending on how frequently we sample this well, right? But if we, again, in a commingled scenario, sometimes we want to answer these 3 particular questions, right? So the first question is what? Right, so what fluid? Is it oil? Is it gas? Is it water? Right? Is coming from where? Is the second question. Is 100% coming from the upper perforation or 100% from the bottom? Right? Or imagine if it's coming from somewhere in between, a place that is not perforated. So in this case, could be the scenario of a leak as well. Is it do we have inflows at the gas lift valves, right? Are the gas lift valves active? And then how much? The how much part is the quantification, put numbers, right? So barrels per day or cubic meters per day, right? So these are the objectives of production log. So if we are successful at acquiring and interpreting the logs, we should answer these 3 questions, and the typical way to answer is in production profile that may look like this, right? The colors indicate water, oil, and gas, right? In this case, we have 4 perforated intervals. And for example, in this particular case, we can see that mainly these 3 bottom perforated intervals produce water. There we go. Produce water. So in this case, the production log could help us to, for example, set a plug at this particular depth and get rid of the water, decrease the PWF, and possibly produce more hydrocarbons from up here. Okay. So these are the objectives of production logging. So what tools are we going to use to achieve this? And here you can see a PLT in a producing well. If you see, the PLTs are modular tools. So here you have a module, the spinner module, right? The flow meter. Then here you have a separate module, and then another one, right? So you may wonder, what tools do you need to run in whole to achieve the previous objectives, right? What fluids come from where and how much, right? And the minimum depends on the number of fluids, right? So the easiest is to start with a single phase flow. If you imagine single phase flow, this well here looks like a multi-phase, right? But in a single phase flow, we need to answer just solve just one equation, right? This equation is the total rate at any depth. That is basically the fluid velocity, like we'll call it VM, as average, or later will be a mixture, times the area of the pipe, right? So I need to know the fluid velocity. And for that, in the industry, we typically use spinners like these ones. These are two types of full bore spinners, right? Cage spinners. This one can only go at the bottom of the tool string. We typically tend to add a second spinner, a backup spinner that can go here in between, We will call this one the inline, right? That in case this one fails, we will still have sources of velocity. This, if you see, is basically like a turbine or a little fan that rotates. This rotation is what we will call revolutions per second, and we will convert those revolutions per second to fluid velocity, that is the required input. Okay, so that's the first. For single phase flow, we could handle it with a spinner. We will see later that we will still need to add other things, right? But the spinner is the key, right? Now, what happens if we have a two-phase flow? Well, this total rate now is composed by, let's imagine, oil and water, right? So this means that we need to split the total rate into the two phases. So we will need to say the percentage of the pipe occupied by the different phases. And typically for vertical wells, for conventional PLT, something very typical is to add a density tool, right? Density tool will basically measure the mixture density. The mixture density, imagine an average between the water density and the oil in this case, right? And from that, we will know how much of each we have, and we will be able to calculate at any depth these two, right? So for two phases, we need at least one, we call it fluid identification tool. For three phases, now we need, apart from the velocity and the density tool, we need a second independent source of fluid identification, because now we have the third phase. Let's imagine here would be we add the gas, right? And therefore we need, it's not enough to split for example, the density into the mixture density, but we need two independent fluid identification tools. Okay, so these are the necessary tools, right? How do we run this PLT? How do we acquire this data? And many of you may come from the open hole side, right? That in open hole, we typically run a single pass. Or maybe we run one pass and then a repeat section, right, in an interval of interest. Here we do it slightly different. If you see here, we have a gamma ray cable speed. If you see cable speed, we have a 0 and then positive values when the tool goes down and negative when the tool goes up, right? Spinner in RPS, pressure, temperature, and this is a density tool. So if you see the run sequence, we go down, right, at certain cable speed, then we go up, right? For example, 10 meters per minute down, 10 meters per minute up. 20 minutes down, 20 meters per minute up, right? 30, right? And 30 up again. And then in this particular case, 40 up and 40 down and 40 up, right? So if you see, we end up with 4 down passes, right? On the positive side, remember, it's down passes. And on the negative side, also 4 up passes at different cable speeds, right? And we don't acquire this in total 8 passes to have just redundancy in the measurement. Some measurements, if you see the density, all the 8 passes are overlaying, right? In this case, the well is fully stable. In the case of the pressure is not stable, so then the passes are not overlaying. But we acquired this number of passes because we need to go from this spinner RPS to fluid velocity, right? And then as the spinner reacts to the relative fluid to tool velocity, we need to acquire this RPS at different cable speeds, right? So, for example, something interesting of these spinners, right? The spinners is that are fluid dependent, right? So imagine the spinner manufacturer. You will have in these webinars other different manufacturers. You put this spinner in a pipe, in a flow loop, and you are able to pump at different flow rates, right? Or different fluid velocities. You are pumping water, you have a perfectly calibrated pump here. So you have a fluid of a known density and known velocity. And you will be able to construct a plot like this. So you will be able to measure here the RPS of the spinner, right? This spinner rotation is in the vertical axis, and on the horizontal axis here is the mixture velocity that you are pumping, right? And if we do it in the lab, you will see that it behaves linearly, right? It behaves linearly like this, straight lines, but the slope of these straight lines depends on the fluid type. And if you see, for example, here it's telling us there is an ideal curve or line, and it shows us that if we have, a very low fluid velocity, in the ideal case, imagine this is really, really small, right? Some liters per hour, right? Something very, very small. Even at a very small velocity, we would be able to, the spinner will rotate, right? But the reality is that it doesn't, right? We need to overcome certain minimum fluid velocity, this one, certain minimum fluid velocity. If we don't reach this velocity, the spinner does not rotate. How do we call this velocity? We call it the threshold of the spinner, right? The threshold of the spinner then is the minimum velocity for the spinner to start to rotate. And on the other side, we have how much the RPS increases with the increase in velocity, that this is the slope of the calibration crossplot, or simply we call it the sensitivity, right? So the sensitivity relates the change in measurement with respect to the change in the input parameter, that is, in this case, is the fluid velocity, right? So this is how it behaves. So if you see here, we will need to see in our particular well, what are the downhole fluids, right? In our wells, imagine we have a three-phase producer. Well, depending where the spinner is immersed at deeper depths, may be in water, then it may be in a mixture of oil and water, then in the three-phase, it means that the spinner will behave differently. It will have different slopes and thresholds. So for example, let's see in this case, right? Can you see we have a spinner and a cable speed and a density. This is a density tool called gradient manometer, right? We're going to do this calibration crossplot, right? That is has the RPS on the vertical axis and the cable speed on the horizontal. We cannot do at downhole conditions the mixture velocity on the horizontal, because can you imagine you being in charge of one of these logs and asking your well operator okay, now produce the well at 10 meters per minute, then produce the well at 20 meters per minute, then at 30, right? They are going to laugh at you, right? It's not possible to control the well in such a way. So what we do, using what we learned, that the spinner reacts to the relative fluid to tool velocity, fluid minus tool velocity, we do something like this. We acquire the spinner RPS at different cable speeds, right? And remember that the spinner will react differently for the different densities. Can you see here 0 to 1.2, meaning that towards the bottom of the well, below this perforation, is a heavy density, like 1. So here we may have water, right? Here maybe like 0. I don't know, let me say 0.7. So maybe here we have grams per cc, right? So maybe this is an oil, and in here we have a 0.4, right? And this may be a mixture of oil and gas, right? So imagine we have this scenario. It means that the spinner will behave differently in the three intervals, differently in regards of a different slope and a different threshold. So if we calibrate here, what it means calibrate, well, we will measure for each of the passes, right? This is the first down pass, so the cable speed and the RPS. So in this interval, in the calibration interval, what we will do is to plot this here, right? So we plot the points. Can you see the plot? The points are here. This would be the first down 1, then this is the down 2, and so on, right? All the down passes on this side, on the positive cable speed, remember, and the negative, so this is the up 1, and so on. So the software will read these values. What happens if we draw a line? Well, you can see that at some point, if we continue going down in RPS, right, RPS will intersect the x-axis, the cable speed. So 0 RPS for this cable speed. So in what if you think about what situation may lead to 0 RPS, in this case, we are 0 RPS, and we are reading a cable speed, right? So imagine minus 45. What it means, this minus 45? Why at minus 45, right? Remember, negative is cable going up. Why at minus 45, the spinner RPS could reach 0? Well, think about if you go up at 45 meters per minute, your spinner, it won't rotate, right? If it doesn't rotate, why may be the situation because it doesn't rotate? Well, because remember that the spinner reacts to relative velocity, fluid minus tool, right? So there is no relative velocity, right? There is no relative velocity. That's why it's measuring 0, right? Meaning that you just found what is the fluid velocity at this particular depth, right? If you extrapolate to RPS equal to 0, that tool velocity, the tool velocity here, that is the cable speed, is the fluid velocity, okay? But it's not just that, but remember that in the previous slide, we saw that there is also a threshold, right? So if here we subtract the threshold, we obtain what we call the apparent fluid velocity, or the velocity as seen by the spinner, right? So this is how it could be the calibration, for example, for this upper zone. We can repeat, we have to repeat this in all the zones, right? For example, in the middle, we plot the points here. You can see now we have positive and negative, right? That's why it looks like this, positive and negative RPS. And then if you see here, there are different slopes, the slopes and the thresholds. Well, maybe here they look perfectly parallel, but they don't have to be perfectly parallel. So, but there are different slopes and the threshold and different threshold. If we extrapolate again here to RPS equal to 0, right, we reach this scenario again when where there is no relative velocity, right? The tool velocity is equal, the tool velocity, remember, as given by the cable speed, is equal to the fluid velocity, right? So this is how you could, let's say, visually understand this calibration crosspoints and how to go from RPS to fluid velocity, right? The velocity will be somewhere in between, right? Because remember that apart from the velocity, the intersect, sorry, you need to add the threshold, right? And similarly, from this bottom spinner calibration zone, where you will reach 0, when you add this distance, it will be 0, exactly 0, meaning that in this bottom section, we are in a 0 fluid velocity environment, what we call a no-flow zone. Right? So we will start our example with that. Remember, the key here is to go from RPS and cable speed. Through calibration, we will obtain something called apparent velocity. If we have the velocity, right? If we have the velocity, we can quickly move to rate. This is rate in barrels per day, right? Because we know that the total rate at any depth will be this velocity, right? We will measure this velocity point by point. So this is the, it's not exactly this one, but let me call it the mixture velocity. If I have time later, I will explain, times the area of the pipe. The area of the pipe, most of the time, we are quite certain. We can use pi ID squared divided by 2. By 4, sorry, or if we are in an open hole environment, in a barefoot completion, for example, you may want to use an XY caliper, okay? Good. So let's get started with Emeraude right now. Until now, we know how to obtain a single phase scenario, right? But our case will actually be multi-phase, right? So let's do it. So this is Emeraude. For the ones of you who didn't know it, we will start by creating a new interpretation. This is just a single flowing survey, what we are going to do. So I'm going to call it flowing. And this well, we have some surface rates. Can you see surface rates and conditions? These are not mandatory, but if you have a test separator or, hello, yeah.
Sorry to interpret. Just some people may wonder how they will get license for Emeraude.
Sorry, say again, Masin.
Some people may wonder how they will get a license for Emeraude.
Well, if depending on the work, many of you work for companies that have one or several. I've seen the names, and many of the participants work for companies with.
Yeah, I mean temporary license.
Okay, temporary. Yeah.
I believe they sent email to KAPPA and they can get this 1 month license if they want to practice.
Yes, correct. We have the 1 month demo license for not non-commercial purposes. Yes.
Yes,
Correct.
so they can practice the Emeraude and other software. Okay, thank you.
Yes. As I was saying here, the surface conditions and rates, these are, if you have surface rates, better. Otherwise, it's not a problem. It's not mandatory. In this case, the well produces 2,700 barrels of oil and 4.5 million standard cubic feet per day of gas. Okay. Emeraude is structured in, if you see here, there is a ribbon structure with a number of tabs. The main tab is from where we are going to load all the data, right? So we are going to start by defining some well data. In this case, click here on details. There is a deviation. This particular well is perfectly vertical, so I'm going to skip this one. Internal diameter, simply here I'm going to enter 6.184. This is a 7-inch casing. Roughness, right? There are a number of tools that require corrections for frictional pressure drops, and these are a function of the roughness of the pipe, right? So you here, if you don't know what is the roughness of the pipe, you click here on compute, and you will see a table with some typical values. This case is also asking for the diameter, and so on. There we go. We calculate the relative roughness. Then in this particular case, we have 2 perforated intervals. I'm going to enter these intervals here, right? These are our 2 perforated intervals. And that's it. We are not going to add markers. You could add geological markers, mechanical markers, let's say, of the well, where the depths of the packer sliding strips and so on. In this case, it's a very simple well completion. Can you see here, we loaded from details. This is the well data. We can load open hole logs. We can define a well schematic, but let's go straight to the PLT data, right? Can you see we generated the first 2 tracks, the perforations and the ID. We are going to load some data here. Click add. And here you can see there are 4 down passes and 4 up passes that I'm going to select them all in one go. Click open. And based on the mnemonic, Emeraude will identify, for example, if Emeraude reads grad, it knows that it's a density tool. Spin, it knows that it's a spinner, right? A flow meter. So there are, we have predefined mnemonics, right? Otherwise, if the mnemonics of your tools are not identified, you will have to do it manually the first time. So all good to load. I'm clicking import here. and the data is imported, right? Clearly, the scale is not ideal in this case. So there's a zoom and scale toolbar. So if you click on the house, it resets the zoom. To occupy this space, you can move one by one like this, or use these tile plots. There we go. Now we can see much better the logs, and we can start rearranging, for example, things like this. And now we have, for the gamma ray spinner, density, pressure, temperature, tension, and cable speed, right? We would typically save this layout if we like it. We click on snapshot and save this layout. So whenever we want to come back to this, we just to this layout, we just come here and select capture number 1. Okay, so data is loaded. The last thing I'm going to do, tool information. Remember, we loaded this, and sometimes we need to provide some well information. For example, if you use density tools, you need to identify the type of density tools. In this case, it's a gradial manometer, and a spinner blade diameter used for some velocity corrections is 3 inches. Good. So we loaded the data. And before going to the calculation itself, we typically start from the quality check, right? So here is the point of the interpretation where you need to be very structured, right? Typically, you would start from the gamma ray, right? We will load an open hole gamma ray or a CCL and some completion description. And if you see here, there are a number of depth matching or depth correlation options, right? In this case, we are going to skip this part, but if you see here the gamma ray, this is the first thing you would do, right? To make sure that the passes are on depth with the reference, or at least among each other, right? In this case, all the passes are on depth, right? Gamma ray is also used as a primary indication of things like radioactive scale deposition, and so on. In this case, if you see, it goes from 0 to 100 API, so we don't suspect of anything. And as I mentioned, typically we would do a quick quality check. Remember, for example, we open the cable speed to remember that we have 4 down passes. Remember, the down passes are positive. You can use the eye with the eye pointing down or up. If I uncheck the eye and the arrow pointing up, if you see, removes the up passes. And then if anything looks like noise or not a real measurement, we need to do something. So for example, here, this pass, if it has high amplitude noise here that is not representative of the cable speed, we can activate the measurement by using this pick nearest, and then we can use one of the editing options, for example, hide parts. There we go. And this data here that has been grayed out is not going to be used for any calculation, right? In production logging, whatever is not real, right, is noise, and you cannot use it you shouldn't use it for interpretation. We have the tension, the pressure, for example, here. Can you see pressure will be used for computing the PVT properties? We need to know the densities, the formation volume factors, the viscosities, and downhole. So PVT will be initialized with this. So here, the pressure is, if you see, it's showing some gradients, but it's showing that the passes are not overlaying, telling us that the well was not fully stable. In production logging, we want to be as stable as possible, right? Otherwise, we don't have a single snapshot at the time, but we have a changing profile. But if you see here, these gradients also tell us something about the density distribution, right? Although I have a proper density tool, I can come here to pick nearest, click on pressure, right? I activate any pressure. And we can do the derivative, right? If derivative, if for example here, if we have what we want to do, the dp, right? if we consider only the hydrostatic component, we know that this is the gravity, mixture density, right, and set, right? So if we do the derivative of dP over dz, we would obtain this mixture density. That is what I'm going to do right now, right? So I add a smoothing window of 4 feet, for example, and there we go. Can you see here on the right, I have a new track called dPdz, right? In units of density, that shows basically what is the fluid distribution, right? Towards the bottom, we have like heavy fluid, like 1 gram per cc. Here we have something 0.6 and so on, right? So can you see this is remember that this is an oil and gas well, right? So we have water in the sump below the deepest perforation, but here it goes to the oil density, right? It's like 0.65, and then here it goes to 0.5, right? So we are starting to see what fluids are in this well, even without looking at the proper density tool. That, by the way, they are very similar, but the actual density tool has a better data quality because it's not affected by things like unstable well conditions. If you see here the temperature, it is quite noisy, electronic noise. Temperature between up and down passes has some hysteresis. I'm going to uncheck the up passes. So here are only the down passes. If you see how this temperature behaves, is basically, I'm going to draw a line here. Let me move this here. I'm going to draw a line. There we go. And we see at the bottom perforation, we see warming, and at the upper perforation, we see cooling, right? I'm not going to go very deep into this, but you might remember that gas expansion from the reservoir into the well produces Joule-Thomson cooling effect, which looks very much like this strong cooling, while this warming, on the other hand, is more indicative of liquid production, right? So even as mentioned before, we are looking at the pressure and the temperature, and these agree, right? So from water, non-moving water at the bottom, we go to, we see a warming, which indicates liquid inflow, and then the density goes to 0.65, so mainly oil filled, right? And then here we see the cooling from gas production, and the density goes from 0.40 something, which indicates a mixture of oil and water. Oh, oil and gas, sorry. Okay, let's move on. Next thing is we finish with this quick quality check. We understand now the productions and so on. The spinner needs to be converted into a fluid velocity. So I'm going to click here on information to create the first interpretation. This will be, we require reference channels for interpretations. There are 8 passes, right? So the objective of the reference channel is to tell to the software which of these 8 passes is the one of best quality or is the most representative of the downhole conditions, right? So if you click here on temperature is always best to select slow passes, right? When you want to have better detail, you do slow passes, and in down passes, okay? So down number 1. Pressure, in this case, is quite unstable, so I'm going to select all of them just to get an average. And density, if you see, is quite very, very stable, so I'm going to also select any of them, right? One or all is the same. There we go. So this is the density. Let me just remove some tracks now from here. There we go. I put the density next to the spinner. And why I do this, because if you see now, once we are in this left panel, that is the interpretation panel, we just need to follow the options. So the first option here is spinner zones. We need to define the spinner calibration zones. Remember, the spinner will behave differently for each fluid type. So use the density to identify the fluid types. So one density here, right? The mixture, the oil 0.60 something here, and at the bottom we have water, right? So this particular case, remember having 3 spinner calibration zones. When you come to the calibration crossplot, there will be 3 lines, right, that you can activate using this option, right? And then the objective was to find the slopes and the thresholds, and from this, the software will calculate the fluid velocity. So through regression, the software gets the slopes, right? For example, for this zone, it got the slope here. So in this case, I'm going to, and then being a low flow zone, this intercept correspond to the threshold. So I come here to the threshold and set this as my thresholds. In the middle zone, right, there is fluid movement, so you cannot calculate the threshold in the same way, right? The threshold in this way, you can only calculate it in 0 fluid velocity. But remember that the objective is here to go from fluid velocity, from RPS to fluid velocity. So whether you come from this positive line or from this negative line, the fluid velocity has to be the same, right? So, so what we are going to do is use an option that takes this separation and divides the gap by 2. That is this one. There we go. And up here, there is a zone that all the RPS are positive, so you cannot calculate the threshold in any of these ways. Here you tend to use rule of thumbs. I can come back to this later. Just let me enter a value of 14. This is basically a multiplier of the slopes that the threshold that I got at the bottom zone, right? So we click OK here. Once the slopes and the thresholds are computed, right? Slopes and thresholds are computed. You see this apparent velocity. It can be calculated by a simple equation, right? The apparent velocity as oops, B, this is a P, B, A, P, P, as seen by the spinner, is the RPS of the spinner measured at any point, right? So point by point, the software will measure the RPS divided by the slope. The slope is what we just calculated in the calibration crossplot, minus the cable speed. Again, the cable speed is a measurement, so point by point, the software will get each value, and then plus the threshold of the calibration crossplot, right? So this is, once we calibrate, we would be able to generate an apparent velocity even just by considering one slope, one pass, sorry. In this case, we're going to use all of them, and let me click like this, and there we go. Can you see I have a velocity match here that we went there from RPS to final velocity, right? One more thing is that, as mentioned, we to calculate the apparent velocity, we use the slopes and thresholds from the calibration crossplot. But here, in this case, we have 3 different slopes and thresholds, right? Through these orange zones, you can say what's the interval, the application interval for each of the 3 set of calibration parameters, right? So I'm going to use this zone like this. And if you see, I'm using the density as the reference, I'm extending the calibration zones based on this density and on the interfaces, right? So here I just need to regenerate the apparent velocity, and there we go. So this is a good apparent velocity, showing 0 fluid velocity, a certain velocity here, and of course it increases even more, right? So we are nearly there. So with this, remember, we are ready to compute the single phase velocity, but this well, single phase, sorry, the total rate, right? But this well is not a single phase well, right? It produces oil and gas, right? So what happens when we have multi-phase scenario, right? So in a situation like this, imagine that you make here. Well, in this particular case, there is oil and water, right? And you make a cross section at certain depth of the well, and start counting the area that the oil occupies, right? Imagine that we can somehow count the area that the oil occupies, and we plot it in something like this, right? So we will see here that the oil occupies 25%, the water 75%. How do we call these areas? These are the holdups, right? So the holdup of the oil is the area occupied by the oil at certain depth of the well, or we can talk about volumes of well. If you talk about control volumes, it's the volume divided by a total control volume, right? And why do we need these two? Well, because now the two rates that we want to calculate, imagine we want to calculate the oil rate, sorry, this is the water rate, now is the velocity of the water times the area of the pipe. But now, if you see the water does not travel across the full area of the pipe, but occupies a fraction that is the water holdup, right? Similarly with the oil, right? So what tool can we use to the oil velocity area, but the oil again occupies the area of the oil. So what tool can we use to compute these areas, these holdups of oil and water? Well, something that we can do is, in this case, what we have is a density tool, right? It's a mixture density tool. We put a density tool here, and this mixture density, this gradient-manometer in our case, imagine the mixture density tool will be influenced by the density of the oil and the density of the water, right? So it will be the density of the oil times the area occupied by the oil, the holdup of the oil, plus the same for the water, right? So that's how we are going to get the holdups, right? That's why we run a density tool, because it helps us to make the split, right? And from where do we get the density of the oil and density of the water? From the PVT, right? So in this case, I come back here, I enter the PVT, right? We are dealing with a saturated oil. So in this case, the solution gas oil ratio is 1,100. I go to the gas here, it's a 0.7. I go to the oil, and it's a 38 API. This is a black oil PVT, right? So it uses PVT correlations, standing correlation, right? Standing is a correlation that, if you see the title, is called like California black oil. So it was created with certain samples, right? So it means that may not be perfect for our well, right? Our fluid. So it predicts some densities, right, as a function of the pressure and the temperature. So you can constrain this. I'm going to click here on the constrain option and say that at certain temperature and at certain pressure, I know the density value, right? That is 0.68. There we go. And then if I think someone needs to mute. There we go. So here we just constrain the prediction of the PVT. Okay. Good. Okay. So if you see, we are nearly there, but can you see we are missing one more input, and these are the velocities, right? The velocities, the individual water and oil velocities. Because water and oil, or in our case, oil and gas, don't move at the same velocity, right? There is a velocity difference between the two, right? If you open, for example, a soda, you will see that the bubbles will go up while the liquid remains, right? So this means that the bubbles, the gas part, they have a relative velocity with respect to the non-moving water or liquid part, right? And this is what we call the slippage velocity, and this is the last missing part here. So who provides this slippage velocity? So for example, here, let me show you quickly the phenomena. So this is I acknowledge here our friends from Baker Hughes allow us to use this video. Can you see? For example, here you have a horizontal pipe. This is a very particular case of stratified flow regime with water and oil, right? But as mentioned here, can you see this? It's 1,000 barrels of water and 1,000 barrels of oil, right? In a perfectly horizontal well, 90 degrees. You can see that in this case, well, they occupy what the concept that we just learned, the hold up, each of them occupy 50-50, right? The water cut is 50% because there is 1,000 barrels of oil and 1,000 of water. And the hold up in this particular case is also 50%, right? But look what happens if we change the deviation, for example, 1 degree. Can you see the rates are the same? So the water cut is the same. We just change 1 degree downhill. Now look at the water hold up. Can you see? Now the water occupies only maybe less than around 30%, I would say, and the oil 70. And it occupies 30 because the oil is moving, the water is moving faster. If we go the other way around, 89, 1 degree uphill. Now the oil occupies a smaller area because the oil moves much faster, right? So the relative velocities keep changing, right? The relative velocities that what we call the slippage velocity keep changing, right? So remember, what we know at this depth is the velocity and the density, and we want to obtain the final results, right? So we want to know the final results, meaning the individual rates. So for this, we measure the velocity and the density or the hold ups, right? But we are still missing this, right? To have a closure of, let's say, all the equations, we are still missing the slippage velocity. Who will provide the slippage velocity? Multi-phase correlations, right? In Emeraude, let me skip this one, but in Emeraude, we will use different slip correlations that will identify the flow regimes. Something important is that in multi-phase conditions, in oil and gas travel in an immiscible way, and this the relative fluid velocity, the gas minus oil velocity in this case, will change depending on the way the fluids are arranged, that this is called the flow regimes. So can you see here, bubble flow, dense, bigger bubbles start to coalesce. The gas here becomes a continuous phase. Then at some point, can you see that the gas forms some sort of bullets, right? They are called Taylor bullets. That is typical of slug flow. The bullets break and form this sort of churn. Then finally, at very high gas rates, the gas is the continuous phase here, and then here in the middle, oops, sorry, the gas is the continuous phase, while the liquid forms an annular film here on the pipe wall, right? Each of these scenario will bring a different slippage velocity, and therefore the multi-phase flow correlations many of them predict a flow regime map. This is a multi-phase correlation called Dance and Rose that identify areas, right? This axis here, what you can see, are basically axis function of the gas and liquid velocity. This is specifically called liquid velocity number, so it depends also on PVT. But this is, let's say that this is proportional to the liquid velocity, and this is proportional to the gas velocity, right? So depending on the fluid velocities, the two phases will arrange as bubble, as slug, as mist. So the people who developed these correlations identify this through experimental means, computational means, and so on, and provided equations for this slippage velocity for each of the regions, right? So this is what Emeraude needs now to solve the scenario. So I'm coming back here. The last thing I need to do then, I'm about to solve the problem here. I just come here to Q calculations. And what we need to do now, can you see we have two perforated intervals. So to know how much this perforation produces, I basically calculate the rate above, like here, where I set a gray zone, and below, right? So if I know the rate above and the rate here, the difference is what this perforation produces. And the same below here. Can you see? I know I can calculate how much here is the rate. And then minus here would be the contribution from the bottom perforation. So simply, let's go to the last step. Let me get rid of this so we have more space. We click on rates. We are solving a liquid gas model, and it uses a multi-phase flow correlation, right? If we had more time, we would talk about the different correlations, which will provide different slippage velocity, essentially. So for example, here, let's keep using Duckler. If you see for each rate calculation zone, each of this zone in gray, it identifies what is the flow regime slug, for example, up here. If we go to the middle, is bubble flow, right? So the flow regime clearly changes with depth, right? And with the amount of the proportions of each fluid. And then it provides a slippage velocity, right? So the last thing I'm going to do is just create the production profile, and there we go, right? We create the two typical plots that are the cumulative, that we call it QZT, and the contributions QZI, right? Both are in downhole barrels per day. And can you see here we are applying a match on the velocity. And here is showing, for example, the green is the model, the red is the actual measure or computed velocity. If these two are not matching perfectly here, the velocity, the measured velocity in red changes quite suddenly here, while the one in green, our model, is more progressive, right? And this is because of this perforation. Here, can you see the gamma ray? The gamma ray shows the sand here in the middle, but the perforation is quite big, so it seems like it's perforated even in non-producing intervals. So you can manage this from these blue inflow zones are called. And there we go. For example, I decrease the size of this one. I decrease here again. And then we click on rates. Okay, and you can see now we have a much better description. We know that only a small percentage of the perforation produces. The results are also seen in the summary table in terms of downhole rates and surface rates. So for example, here for each of the inflow zones, you will see the oil rate in downhole barrels, surface barrels, the percentage, right, of each phase, and the same with total fluids and everything. Okay, so these are the two typical ways to export to present the data as QZT and QZI, and the tabulated results that you would use to make decisions, right, of what you want to do with your well. In this particular case, there was no particular like objective of it's no water shut off or anything. It was just reservoir description. Okay, so this was a two-phase case in a nutshell, right? Very quickly. There is much more in terms of quality check, in terms of application of multi-phase flow correlations, but for 1 hour, I think this is enough. So we have some time for questions. As mentioned previously, my email is kotlar@kappa.com. For any question or comment, please don't hesitate to contact me. Okay. So Masin.
Yeah, that was like a great lecture for productory regarding to Emeraude. For sure, we put it on YouTube. Okay, so it will be a reference lecture if somebody wants. Okay, and further details, uh, I highly recommend to join one of the official KAPPA courses, either online or physical courses. They publish, sorry, they add for them using their website and using. Also, if you subscribe for KAPPA letters, okay, and you can get access for let's say login for Kappa website. You will have access for many video on how to video, how to use Emeraude, how to use Sapphire and other, but our focus on Emeraude. And also for sure there is the case toll book. Okay, this is a highly recommended book in regards to all. Yes, this is yeah, this is the videos. Okay, and you can go there and you put your email and try to register there. You can ask for demo from there. This is the video. Uh, yes. What is the, and I believe we put in our advertising the, you can see okay, the
Yes.
videos. Okay, and there is this book. I believe it is the Kappa case toll book, which is, by the way, this book have been updated, I believe, huh? Because when I downloaded, I found it's 5.4, was 5.3.
Just minor. It's not a major upgrade. It was because we printed a number of copies, so we just fix some. There were 2 or 3 typos. There's nothing major, no added topics. So I'm working on the next version that will incorporate electromagnetic thickness and some other things, uncertainty handling and so on.
Yes, that will be great. So if anybody want to jump in, have any question, okay, Steven, I saw you raise your hand. Steven Anderson.
Hello, yes, thank you for the presentation. It was very informative. The fact that we were able to go
Okay.
through an entire interpretation in less than an hour speaks to the ease of use of the software. So my question is, I don't know if you can go back to your last slide with the interpretation.
The Slido or Emeraude itself here?
Yes, the software itself. So am I to understand by making an adjustment to your perforation size, that is what allowed the model to match? So is your comment back to the client that only that little bit of their perforated interval is producing?
Yes, that is a good observation, and that is correct. In this particular case, production logging can also be used as a tool to refine the KH, right? The producing thickness, because at this particular depth is the only interval where we see the increase in fluid velocity, we see the decrease in temperature due to Joule-Thomson and the fluid interface. So all the measurements indicate that the variations of properties or total rate occur there. So in this particular case, as you said, yes, this is something that I could go back to my client saying, the upper perforation produces only from 1/4 of the perforated thickness, and let's analyze why the rest is not producing. In this particular case, I would believe that from the open hole, the case hole gamma ray, we are likely to have shaly intervals here, but in other cases, we need to analyze whether the perforations were really shot at that particular depth and were effective, because otherwise, by reperforating, by acidizing, by applying some stimulation, we may gain, a few feet or meters of producing thickness. That's a good observation.
Okay, thank you. That's a really interesting way of identifying where in the sand you have a positive production from. So that would be very helpful, I think, for future work, even if it's in terms of shutting off a lower zone that's not really contributing. So thanks for that. Thanks for the presentation.
You're welcome.
So we have two questions actually on the chat. One question from Elshad. He's asking which one is better, spinner or temperature, for any flow acidification.
Okay, so temperature, the good thing about temperature is very, very sensitive. If you remember, we talk about some properties of the flow meters, the sensitivity, right? And also the threshold. There is also something else that we didn't talk about, that the resolution. So in general, temperature tends to be one of the most sensitive measurements that we have in the tool string, right? So for identifying small or something else you can do, for example, here the temperature changes are very clear, right? But otherwise, if you have smaller temperature changes, you can come to the temperature itself and apply the derivative, as we did the derivative for the temperature, for the pressure. We can do the same for the temperature. Can you see? Now we have the temperature derivative and see exactly where are the large temperature changes. Sorry, if someone can mute. There we go.
I'm muted.
Okay. There we go. So temperature tends to be very, very sensitive. And something interesting about temperature is that it also feels behind casing, right? Spinner is limited to inside of the casing, but temperature, if you have behind casing phenomena like flow through cement channels, you can also use it. But for the quantification to go from to go and obtain this, the spinner is definitely easier. The going from temperature to flow profile is an inverse problem that requires a fairly good understanding of the reservoir, thermal properties of the reservoir. So it's much more straightforward to use this one.
Okay, thank you. I believe Mohammed Shahid, Mohammed Rada, you can jump in and open your speaker.
Yeah, thank you, Mr. Nicholas. It was a good lecture. But I have one question. You mentioned that the temperature can feel the flow behind casing, channeling, or something like that. What's the effect of this of the flow behind casing on the temperature curve? Is it cooling or heating or what? Can you please
Good.
mention that?
Yes. And it will really depend. Let me see if I can add one slide here. And it will really depend on what's the source. Let me change. Swap. It will depend on what's the source of the fluid, right? So let's imagine here I'm going to do some axis. I'm going to do the temperature on the horizontal, and I will do the depth on the vertical. Sorry, I'm using my mouse and my pulse is not, my hand is not very good. So this is temperature versus depth. Imagine that we have these two perforated intervals. And something interesting when analyzing temperature is to think what would happen when there's no fluid movement. Imagine that there is pretty much no well there, so the formation is still at its original geothermal temperature, right? So in this case, imagine that we would have this, right? The TGO. The TGO is always very important again, because if there are no fluid inflows or outflows, we would expect to the temperature to follow that. So now let's imagine what would happen with a login if these two produce liquid, right? So if the liquid comes from here and come from here, what would happen is that, well, and if I start logging from below the deepest perforation, below the deepest perforation, there is no fluid movement, right? So the temperature inside of the pipe and behind will be the same. So below the deepest perforation, the temperatures will be like this. Now, at this perforation, right, imagine that we don't have channeling, then I will overlap the case of channeling. If you don't have channeling and this produces liquid, the fluid, the liquid coming from here will be exactly at this geothermal temperature, at the TGO at this particular depth, right? TGO at bottom perforation, let me call B, right? And the fluid will enter like this, will enter at this temperature. At some point, we'll start exchanging heat with the formation and we'll try to go back parallel, right? Actually, in the literature, you will find a few methods. One is the Remy method that uses this offset between the geothermal and the measured temperature to calculate, to estimate the rate, right? And then when what happens if we have another fluid inflow from here? Well, we are bringing warmer fluids from below, and then we are injecting fluids or producing fluids at this temperature, right? So the overall temperature will decrease, although it's not a gas, right? It can still lead to a temperature decrease, right? For gas, on the other hand, for gas, we would see the typical Joule-Thomson as we see below, right? So on one side, this is for liquid, right? And on this side is for gas, right? So this is if we have production only from the two perforations. Now, what would happen if there is fluid movement from below? Well, what happens here, imagine that there is bad cement from in all of this interval. The temperature will depart from the geothermal from below, right? Because now we are lifting, even behind casing, we are lifting warmer fluids coming from deeper perforations. So we will feel it like this. It will go out of the geothermals like here, right? So, and there we go, right? Depending, of course, this temperature will really depends on the proportion. So what will generate, especially when coming from below the deepest perforation, is a very marked scenario of departure from the geothermal temperature gradient. Okay.
Okay, great. So let's take our
Thank you very much.
last. Okay, most welcome. So let's take our last question. It's from Shahid, and
Yeah.
he's asking about threshold, how it's come 14 feet per
Okay.
minute, and what's the criteria that
Yeah,
affect the
good.
threshold?
Good point. Okay, this is something that I didn't have much time to talk about, but remember that even here, the only place where we can really measure a threshold is in this bottom zone, right? We need an interval of zero fluid velocity, right? To measure the threshold, right? Because this gap is completely given by this is what is the minimum cable movement for the spinner to start to rotate, basically, right? So what we did in Emeraude is we calculated here at the bottom, right? And then what we do for zones like this that we have no chance of computing a threshold. Well, if you remember this plots like this, your tool provider will have some nominal parameters, right? So can you see here, there are some full bore spinner thresholds. CFB means caged full bore, right? This is a particular type of full bore spinner, right? And you can see that for water, it's pretty much from 1 to 2 feet per minute. Oil is quite similar. For gas, if you pretty much make an average of the oil and of the gas, you will see that you will have to multiply pretty much by a value of 3, right, to go from liquid to water to gas, right? So if from water here to gas, this is like pretty much 3 times, right? So in many cases, you are able to calculate the threshold in the bottom spinner calibration zone that may happen to be filled with water for a water sump. And if up here is single phase gas, this is a way that you can take your thresholds, right? Using a value like this, right? So these are the type of rule of thumbs that I was referring to.
Great explanation. I believe we will conclude our lecture for today. And I highly appreciate the time that Mr. Nicolas Kotlar dedicated to volunteer and sponsor this technical webinar and activity of SPWLA Iraq. I'd like to thank our attendees as well. And keep tuned with us for next webinars. And there will be more webinar from KAPPA in September regarding more complex tools. Thanks, Nicholas. Thanks, our attendees. Dr. Mohammed, if you want to say last word.
Yes, Mr. Mazen, thank you, Mr. Nicholas, for your great presentation. We hope to see you again in SPWLA chapter, Iraq. And thank you, everybody who attended to the third webinar today. Thank you, everybody, again.
Okay, my pleasure, and looking forward to seeing you in September.
Thank you, Nicholas. Thanks, everyone, and have a great day.
Thank
bye
you,
bye.
Nicholas.
Thank you, Mr. Mazen.
Thank you. Thank you.
Bye.
Bye bye.